Good day and welcome back for the fifth and final installment dealing with derivatives and rates of change. In this final video, I would like to focus in on two more examples where we're investigating the interpretation of the derivative as being an instantaneous rate of change. And let me give you the reminder going all the way back to the initial video for this section. F prime of A, the derivative of f at the specific value of A, represents or can be interpreted as the instantaneous rate of change of a function f with respect to x when x is equal to a. And something that helps me when I'm working through the examples, like we're going to see in a few minutes, is that I think of this as the instantaneous rate of change of f, which is whatever our output is, with respect to x, where the x is really representing our input, but specifically when that input is a. So let's see if we can take this interpretation and use this idea to investigate what I would consider a very common example. So we're given the following information. Fuel consumption of a car, thinking in terms of how many gallons per hour, traveling at a speed v, miles per hour, is given by f of v. That is to say, we're thinking of f as being a function where we input the speed of the car, and what we get out is its fuel consumption, how many gallons are being used per hour. So let's go ahead and see if we can use the statement above to explain the meaning of f prime of v. And all I'm going to do is take that above statement and I'm going to rewrite it in terms of the given information. And this is most definitely the type of problem that at first glance I think seems tougher than it really is. So we're going to take that above statement, put it into our specifics. So f prime of v is the instantaneous rate of change of f. And now note, I'm not going to write down f because that's very generic. I want to make this specific in terms of our above information. So it's an instantaneous rate of change of whatever our output is. So that would be fuel consumption. With respect to whatever that input is. So I'm not going to say v, but I'll say the speed v of the car. So note this is precisely what we have above. F prime of v is an instantaneous rate of change of the fuel consumption, which is the output of the function, with respect to speed, where speed is the input of the function. Now, note we are really asked to do two things here. One, kind of use a sentence to explain the meaning, which we've done. And secondly, we've been asked to determine the units. So in terms of units, we're going to have something over something. And the language really tells us exactly what this is going to be. The rate of change of the output with respect to the input. So we take whatever the units would be for those outputs, and that's going to become our numerator. So fuel consumption is measured in terms of gallons per hour. And then we take whatever the units are of our input, and that becomes our denominator. So miles per hour. So finally we end up with gallons per mile when we cancel off those hours. Now let's get even more specific here. Let's use a sentence to explain the meaning of this expression f prime of 20 equals minus 0.05. So remember, f prime of 20 is going to be a measure of the instantaneous rate of change of the fuel consumption with respect to speed when the speed is 20 miles per hour. So at a speed of 20 miles per hour, the rate of change of the fuel consumption is going to be negative 0.05. So that would mean it's decreasing at a rate of 0.05 gallons per mile. So let me go ahead and put that into words. So at a speed of 20 miles per hour, the fuel consumption is decreasing. And note the decreasing is because of the negative, and that's really telling us it's a rate of change. So we could say the rate of change of the fuel consumption is, or we could note that the fuel consumption is simply decreasing and then include the rate. So it's decreasing at a rate of 0.05 gallons per mile, which gives us our first example relating back to this interpretation of the derivative as being an instantaneous rate of change. And I very much realize that when we see this very kind of vaguely defined function and statement in our example, these are not easy problems to work through, especially the first couple times, which is why we continue practicing. So with that in mind, let's look at a second example. What we are told for this second example is that h of t represents the daily cost in dollars to heat an office building when the outside average temperature is T degrees. So when that average outside temperature is T degrees, h of t represents how much it would cost to heat the building for the day. What I would like you to do now is to pause this video and take as much time as you need, 3, 4, 5 minutes, and see if you can look back over our previous example and use that idea to answer the following two questions. Okay, so assuming you have paused your video and worked on this for a few minutes, and remember, if you haven't and you want to take the most you possibly can out of this, do so now. Pause the video, take a few minutes, hit play. Okay, so let me give you my sentence explaining this. So once again, we're thinking this is going to be an instantaneous rate of change, or you can even just write rate of change is fine. So I would say the rate of change, it reads a bit more naturally that way, of whatever our output is. And note the output is the daily cost to heat the building. So I'll just say daily heating cost. So the rate of change of the daily heating cost. So that's our output. With respect to the input, so this would be respect to the average outside temperature. So once again, that's the input. And this is specifically for 58. So this is specifically when the average outside temperature is 58 degrees. So the last part is kind of the specific input. And note if you can kind of keep this template in mind, the rate of change of the output with respect to the input when you're at a specific input. So think of that as 3 blank spaces that you kind of fill in, and that will allow you to complete any of these problems. Now note we're additionally asked to determine what are its units. So let me just kind of note to the side what the units are. So the units, whereas we noted previously, the language really tells us kind of how we are going to determine these units. So it's the rate of change of the output with respect to the input. So we take whatever the units would be for the output, dollars, right, the daily cost, and we divide it by whatever units are used for the input, which is degrees Fahrenheit. And I am perfectly fine with you using a dollar symbol or writing it out in words. So really whatever is most convenient for you. And then lastly, we're asked, do you expect h prime of 58 to be positive or negative? And let's think about this as intuitively as possible. If you are thinking about the heating function itself, in general, you might think as the outside temperature increases, so if it's warmer outside, your heating costs should go down. So if we think about what this derivative is really going to be measuring, or what it's going to tell us, it's a slope of a tangent line. So if you consider the tangent line to this heating curve when the average temperature outside is 58 degrees, it should be something with a negative slope. Because as the temperature increases, the cost to heat the building should go down. So the answer that we should have here is that it should be negative. And the reason being, and note we should always make sure that we give an explanation, is because as the outside temperature increases, the heating costs decrease. And it's really that decrease in the heating cost that will tell us that h prime of 58 should be negative. So that completes our discussion of derivatives and rates of change. But in our next section, we will continue a very similar line of exploration where instead of thinking of a derivative specifically at a point, we'll investigate a derivative as a function. So make sure that you're practicing suggested problems. Also, when you have questions, do not hesitate to reach out. Stay tuned and take care.